So this first video clip is motivated by me working with my son when he was in algebra, and he was trained that every time you saw parentheses, distribute, right? Sometimes that's a good rule of thumb. Other times it makes far more sense to solve the equation by starting with division. And I understand why teachers don't like to do that, because we teach kids that when you're equation solving, we've got PEMDAS, and so we reverse the order of PEMDAS, and so we do this, and then we do this when we're solving equations. So I understand why teachers hesitate to teach kids that you could start this equation by dividing both sides by 3. And I was very against the fact that my son just acted like, oh, no, I have to distribute first. I can't do it any other way. I also understand that when you teach students only one way, it does improve their short-term procedural fluency. All right, but when you show kids multiple ways to do things, I understand they'll say, oh, well, they might go home and do their homework and get confused on their homework because I showed them 2 different ways. It is better for short-term procedural fluency to give them one strategy. However, you will improve long-term conceptual understanding if you show them more than one strategy. So I think that this balance scale approach is perfect for helping the students understand why it is that we can divide both sides by 3. Okay, so notice how I have 3 of these equaling 27. And so on my balance scale, I could say, well, if I took 1/3 of this, right, because this is kind of like my x plus 7. I could think of my triangle as my x and my oval as my 7, right? And I could show them why then just these 2 together would have to be 9. All right, so I love the balance scale approach for a couple things. One of them is going concrete to abstract. Another reason is it helps build conceptual understanding of equations. So next page, okay, so then up here I got a little more abstract, all right, by using x's and 7s, right? But again, I could help students to see that if I broke this up into thirds, if I took 1/3 of what's on this side, right, then I only have 1/3 of what's on the other side. So I got a little bit more abstract. So again, I'm building very carefully from the most concrete to a little more abstract, and then equation solving without any of these supports, like the balance scale, would be the most abstract method. Now I understand teachers don't want to teach kids start by dividing, because then you'll come to something like this and students will try to go like this. Oh, okay, you told me I could divide by what's in front of the parentheses, so I'm going to do that. All right, that would not surprise me as a common mistake that students would make. All right, so again, showing this on the balance scale, right, I hope would help with that. Okay, I can't divide this in half without also dividing this in half, right? What I do on one side, I have to do to everything on that entire side. All right, so hopefully students would be able to recognize when they looked at it in this concrete way, they'd recognize, oh wait, I have to deal with the 1 first. After I deal with the 1, then I can take half of both sides, right? So here I am taking half of both sides and getting 7. Okay. Another thing that is such a common mistake that any Algebra 1 teacher will tell you they see over and over is when solving an equation like this, students see the 1/3, they know they multiply by 3, and they go like that, right? And they forget about the 2. Okay, so they multiply both sides by 3 like that. All right, so to help improve conceptual understanding of why you can't do that, I started with an equation that's in balance, right? And then notice on the next scale, I tripled the x, right? I tripled the cube. Well, if I want to keep this in balance, I have to triple everything. Right? That's how I keep my balance. All right, that shows that in a nice concrete way. I'm going to come back to this equation because when we're solving systems of equations, and well, I'll show you the example on the next page. Well, actually, no, I'll go ahead and do it right now. Systems of equations. So say I'm doing something like this, okay? I actually do this when I teach Math 213, which is applied calculus, calculus for business majors, and we do a little mini ELA section in it. And I'm drawing pictures like this even with my college students, all right? And I'm showing them, why is it legal? You know, I'm talking to them about what are legal things that I can do and why are they legal? Why is it legal that I can go like that? Right? I could take that second equation and multiply it by 3. And as I'm doing that, I am showing them the pictures of something like this, okay, to help give them conceptual understanding of the legal things that you can do to solve systems of equations. So while I'm on that topic, another thing that we do when we're solving systems of equations is after we multiply through, right, we add them together. Okay, y's drop out. And so again, I would say to my students, why is that legal? How do I know it's legal? And before I start doing this abstract process, I've had my college students looking at something like this, right? And recognizing that if these two are in balance, right? And if I added one side of each balance scale together, right, I would have to come over here and add the other side of the balance scale together. All right, so I am showing students how I can add two equations together and still be in balance. Also, this is great for systems of equations like this. Okay, so we have a tendency to introduce this in a totally abstract way where we tell kids, okay, this is y, replace y with its equal, right? But if x were a square and y were a triangle, right? And then I had this equation over here, I would be talking to students about how over on the left-hand side, anywhere that I see this triangle, I can just replace it with its equal, which is 2 squares and a 1. Okay, so I take the triangle, replace it with its equal, and now I've got a concrete representation of that abstract equation. Okay, so one more example that I have on here. A couple different ways I could approach this equation. So if I want to help a student in a concrete way understand the equation 2/3 x plus 6 equals 8. Okay, and so I modeled it here, 2/3 x. A couple different things I could do, right? A student would probably recognize, okay, take 6 off both sides, and so then you get this this 1/3 x. Each 1/3 x has to equal 1. Okay, so I could show it that way. 1/3 of x would have to equal 1. All right, so then what's a whole x? Right, and to get the whole x, I would triple each side. Right, so 1 whole x would have to be 3. Okay, I could model it that way. Or I might have a student who could recognize something like this, if I split that up into like 3 and 3. And then I split my 8 up into 4 and 4. Okay, and then I could separate off my equation like this. This balances. This balances. I want a whole x. So if I want a whole x, how about I add another one of these, right? And so now I've got a whole x plus 9 equals 16. Did I do something wrong? Oh, how about 12? There we go. How about 12? Okay, so I could do different things like that. But again, I've got a nice concrete representation. So I shared with you another what I would call research gift, where I have an article that cites a research citation that talks about why it's good to do these algebra tiles and concrete examples with students. So I hope you will add that to your file of research-based strategies.